In this video, we're going to be talking a little bit about combining sets. And there are logic analogs basically for all of the set operations we're going to do. So the first one is a union, and let me kind of explain what that is. I like to use Venn diagrams sometime to explain what's happening. So let's say this is my universal set. Every element that I want to consider is there. That's my universal set. And let's say A is the set in red. There's A. B is the set in blue. There's B, and there could be some elements in common in the middle. Well, the union is all elements X, where X is an element of A, so it's in A, or it's in B. So it's anywhere in this set here. Let me color in what the union is. I'll color it in yellow. So the union is all of that stuff. And let's just do a very quick example. Oh, I do want to use a pen for this. Let's, in fact, maybe let's have this be a global thing. So let's say A is the set, oh, I don't know. Let's do A, E, J, and let's let B be the set A, B, C, D, E. Then the union of these two sets is going to be all elements that are in either A or B or both. So we have A, B, C, D, E, and J. So we know A is in A, E is in A, so it's going to be in the union. J is in A, and so it's going to be in the union. And same with A, B, C, D, and E. We already have A and E in there, so we just include B, C, and D. So all of these are in the union. The intersection, rather than the or, it switches to an and. We want things that are in both sets. So again, let me draw a little Venn diagram here. Same idea. There's our universe. There's our set A. There's our set B. Now, the intersection this time is going to be the elements in common, that they're in A and B. So that is all of this stuff here. So there is the intersection. And again, using the same example as above, the intersection of A and B is going to be the set that contains everything in common. And you can see here that little a is in A, little a is in B, E is in A, and E is in B, and that's it. So the intersection of A and B is A, little a, and E. Let's continue on and look at a couple of more operations. So here we go. This is the set difference. So it's set A minus set B. And I do want to point out, we are using a minus symbol here. Remember, there are so many concepts in mathematics, we have to reuse symbols. So we know that this means set difference because it's between two sets. That's the way to tell. Okay, so let's draw our two sets, and then let's figure out from the definition what the set difference is. So in our universe, oh, maybe I'll use blue. there is A and B. Well, the set difference A minus B are all elements X such that X is in A, so we're looking for things in A, and X isn't in B. So we're looking for the intersection of A and the stuff not in B. So all of this stuff, whatever's not in B. And if we think about it, that intersection is going to be this stuff here, which again I'll highlight in yellow. So there's the stuff that's in A, but not in B. So that is A minus B. And maybe I'll write that. This is A minus B. And note that B minus A would be different. B minus A is the stuff that's in B that is not in A. So maybe I'll just write this as a little aside. So this stuff here, this is B minus A. So again, with our two examples like on the previous slide, remember A was A, E, J, and B was A, B, C, D, and E. So maybe I'll ask you guys, pause the video, see if you can figure out what A minus B is and what B minus A is. So pause the video, give that a go. Okay, now that you're back, well, A minus B is all the stuff that is in A, but not in B. So we ask, well, here are the things in A. Is A, little a, also in B? It is, so we don't want to include A. What about E? Is E also in B? It is, so we don't want to include E. J, however, is in A, but not B, so we do indeed have J. So A minus B is just the one element set J. B minus A, well, we don't want to include A since A is in A. B is in, little b is in B, but not A, so that's good. We can put that in there. Similarly, C is in B, but not A. D is in B, but not A. And E is in B, but it's also in A, so we don't want to include that. So what we want is indeed just those elements, B, C, D. Okay. The next one I want to talk about is the complement. So the complement is akin to the negation in logic. So it's everything that's not in a certain set. The complement of a set is everything that's not in it. Again, let me draw a little Venn diagram. And this is important where you have to talk about a universe. Otherwise, it doesn't really make sense. So if this is our set A, the negation of A is going to be all of this stuff, is everything in our universe that isn't in A. So all of that stuff. And again, as an example, well, let me make my universe. So let's define the universe here. Let me use a pen again. The universe is going to be, let's say, all letters from A to J. A, B, C, D, E, F, G, H, I, J. So hopefully that's clear. I mean all letters from A to J. Then we already know what A is. The negation of A, actually, okay, I will say some books write it like this. They say the complement is written the same way the negation is, but the book writes it like this, and this is another way of doing it. That's totally fine. The negation or the complement of A. And informally, a lot of mathematicians will just call it the set not A, because it's so related to the logical idea that we'll just call it not A. So it's everything in the universe that isn't in A. So it's going to be B, C, D, F, G, H, and I. So we don't have A, E, and J in there. Okay, let's keep going. The next one I want to talk about is indeed this symmetric difference. And the symmetric difference you can kind of think of as the exclusive OR. In fact, it uses the same symbol as exclusive OR. So it's in one or the other, but not both. Some books, instead of using that, they'll use a triangle to mean symmetric difference. So you might see A triangle B instead of A circle plus B, whatever. But the concept is the same, of course. So let me use my black pen here. Let's draw a little Venn diagram of what's going on, as per usual. So here is our set A in red, and we have our set B in blue. Then the symmetric difference, going by the definition, it's all elements that are in A exclusive OR B. So that means it's in either an A or B, but not both. So let's shade in the Venn diagram what this would look like. So it's going to be it's in exactly one of these sets. So it's not a shared element. So that's what a symmetric difference B looks like. This is A symmetric difference B. Or if you like, A triangle B is another way of writing it. And with our same example from before, remember A was A, E, J, and B was A, B, C, D, and E. Then the symmetric difference is everything that's in exactly one of these sets. So we're not going to include A since it's in both. We're not going to include E since it's in both, but we will include J because it's just in A. And I'll just write that first. Remember, sets are not ordered, so it doesn't really matter. So we didn't include A, we didn't include E, but we are going to include B, C, and D since they're in B but not A. They're in exactly one set. So that is the symmetric difference of A and B. And just a quick note about terminology here. If two sets don't share any common elements, if their intersection is indeed the empty set, if they have absolutely nothing in common, we say that those sets are, and I think I'd scrolled in too much. Let me zoom out here, or zoomed in too much. So we call these sets that's better, we'll go with that. We call these sets mutually exclusive. So that's what mutually exclusive means. They share no common elements. Their intersection is empty. Okay, let's scroll down. Let's do an exercise here. In fact, there are, what do we have here? We have 1, 2, 3, 4, 5, 6, 7 different exercises. Maybe I'll let you guys try them first. So pause the video, see if you can figure out all of these. The first 6 are straight from the definition, so let's just practice with the definition. But the seventh is kind of combining things. So you need to figure out the intersection of A and B, and then take the union with the complement of C, so you'll need to find the complement of C, and then once you have that set, take the complement of that. So that one will take a little bit longer, but it's good practice, so give it a try. Okay, now that you're back, let's figure these out. So we need things that are in A or B. So 2 is in A, 3 is in A, so we're going to include it. 4 is in neither. 5 is in A. Sorry, 5 is in B. 6 is in A. 7 is in neither. 8 is in A. It's also in B, but as long as it's in 1, we count it in the union. 9 is in neither. 10 is in A. So there is the set A union B. It's everything that is in either A or B, or both, of course. Remember, it's a non-exclusive or when we say or in mathematics. Let's find the intersection. It's everything that is in both sets. So we have the 2 and we have the 8. That's it. 2 and 8. Let's do the difference A minus B. Everything in A that is not in B. So let's go element by element. 2 is in A, but it's also in B, so we're not going to include it. We are going to include 3. We're going to include 6. We're not going to include 8, since 8 is in B, but we are going to include 10. So that is A minus B. B minus A, of course, is the other way around. It's everything that is in B, but not A. And from the previous bit, we know 2 and 8 are indeed in both sets. In fact, you can see that from the intersection here. So it's going to be everything outside of that. So it's just the element 5. 5 is the only element that is in B that is not in A. Okay. Well, let's look at the complement of C now. Let's put some equal signs here. The complement of C, well, we have C being 2, 4, 6, 7, and 8. And remember our universe here. In order to talk about a complement, you need to know the universe. And the universe are all natural numbers, such that the natural number is between 1 and 10 inclusive. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we want the elements that are not in C. So 1 is not in C, so we are going to put it in its complement. 2 is in C, so we're not going to put it in there. 3 is not in C. 4 is in C. 5 is not in C. 6 is in C. 7 is in C. 8 is in C. 9 is not. 10 is not. Okay. The symmetric difference. Well, the symmetric difference is going to be everything that is in exactly one set. So we have the elements that are in both sets are 2 and 8. So it's going to be everything but the 2 and the 8. So it's going to be the 3, the 5, the 6, and the 10. Okay, so they were good warm-ups. Now let's do the harder exercise. So we have A intersect B calculated. We have the complement of C calculated. So let's figure out the union of those. So A intersect B, union C complement. So here's A intersect B. Here is C complement. So you can see, in fact, these sets are mutually exclusive. They have no common elements, so we can just write them. No big deal at all. There's 1, 2, 3, 4, 5, 6, 7 elements None of them are shared, so let's just write all 7 elements. So this is going to be 1, 2, 3, not 4, 5, not 6, not 7, 8, 9, and 10. And is that all 7 elements? 1, 2, 3, 4, 5, 6, 7. We got them all. And now we're just looking for the complement of that. So we're looking for A intersect B union C complement, and the complement of whatever that set was. Well, that's everything that's in our universe that isn't in this set. So it's going to be 4, 6, and 7. So this is, of course, 4, 6, and 7. And that's a nice introduction to combining sets. We're going to prove some things about these guys a little bit later. Remember that we can draw Venn diagrams. So let me just show you something that we'll end up proving either in a video or as an assignment question. So if this is A and B, then the symmetric difference is, of course, this guy. So we can think of it as, I want to use my pen for that. We can think of the symmetric difference, if you like, as the union of both minuses. So it's A minus B together with B minus A. So if you want, you can think of it as A minus B union B minus A. A minus B is the left part here. B minus A is the right part. Take the union of those guys. They're mutually exclusive, of course. So that gives us the symmetric difference. Or another way to look at it is, well, it's almost the union of A and B. It's almost that, except you don't want the intersection. So it's everything in the union that isn't in the intersection. So another way to look at it is the union of A and B, but minus the center, minus the intersection. And that's something that we'll show a little bit later.